And let's move to the next speaker, which is Marta Mauri from Zapata Computing.
Hello, everybody.
Hello, nice to see you. So can you share the screen? Okay, so Marta is going to talk about quantum enhanced machine learning with near-term devices.
Great. Thank you for the introduction, and thanks to all the organizers for organizing this nice event and for inviting me to give a contribution. So I'm Marta, and I'm a quantum software engineer at Zapata Computing. And as Enrico was mentioning, I'm going to talk about quantum enhanced machine learning with near-term devices. Let me start very quickly by introducing who we are. So Zapata is a software company, a startup that spun out of Harvard in 2017. And our mission is to build software for quantum computers and develop algorithms for real business use cases, sorry. And our algorithmic efforts span across different industries, namely optimization and logistics, or statistical modeling in finance, for instance, but also materials discovery and quantum chemistry simulations. This is just to give you like an overview of what we do at Zapata. And in order to support the development and implementation of these new algorithms, we built Orchestra. This is our product. It's our platform that is a workflow-based platform that allows us to orchestrate the different frameworks, backends, and libraries and tool sets that are available today in the quantum computing domain. And today I'm going to talk a little bit about how we used Orchestra to implement, develop, and get exciting results in the domain of quantum enhanced machine learning. So let's take a closer look to the problem that we are interested in, namely the use of quantum computers in the context of generative modeling. So what is generative modeling? This is an unsupervised learning task in which the goal is to model a probability distribution of observed data and then be able to generate samples accordingly. So for instance, one could be interested in generating specific patterns, images with the specific patterns, as the one we can see here on the left. For example, there is this bar stripe data set, which is extensively used in the study of generative models, which consist of black and white images of M by M pixel that can display only either horizontal stripes or vertical bars. And this is, for example, one interesting thing, that you can be able to generate images with a certain pattern. But maybe a more appealing application that maybe most of us have seen is the ability of generating faces using generative adversarial networks. So given pictures of people, the goal is to generate new faces that resemble real people, but that are actually fake. And with this, I invite you to check out the whichfacesreal.com website, which is really impressive in terms of the performances that these generative models are able to obtain today. So in a nutshell, given samples from probability distribution, we want to be able to generate new samples from the same probability distributions. And let me stress that this task is a hard task, in the sense that even compared to other machine learning tasks, this is pretty difficult. Like with respect, for example, compared to classification kind of tasks. And how can we understand these is through this example. So you can all think how much easier it is to recognize a Van Gogh's painting rather than actually making one yourself. And so this gives an intuition, at least, of why this task can be difficult. And indeed, the classical techniques that are available today, even though they're powerful, they also struggle for many applications. And therefore, one question that arises here is whether we can use quantum models running on near-term devices to overcome this limitation, or at least to enhance the capabilities that we already have. Let me just stop for a second on why we are interested in quantum computing at all here as a powerful potential candidate for this announcement. So first of all, there are at least two intuitions. So first of all, quantum generative models are provably able to learn distributions that are out of reach from the classical perspective. So we are actually able to explore regions of the probability distribution spaces that are very difficult to reach with a classical technique. And the other motivation is that quantum algorithms, quantum algorithms are can potentially avoid some of the pitfalls that we can have in the classical approach by providing an improved training and an enhanced sampling way, let's say. And so at least these are two initial motivation that makes us hopeful that this approach could be useful. And how do we want to actually do that? So how do we want to introduce the quantum component in the classical machine learning domain in a hybrid fashion? Because we also need to take into account the severe limitations that we, nowadays are there for the quantum hardware. So we want to be NISQ friendly, so near-term devices friendly, and for this reason, we introduce a hybrid paradigm in which we just substitute the classical machine learning model with a quantum machine learning model. This is one of the paradigms that are suggested, and this is the one that I'm going to present today, especially talking about these quantum circuit board machines new method. So what is a quantum circuit board machine? This is a generative model that represents a probability distribution using as a quantum state. So the idea is to approximate any arbitrary distribution in a NISQ-friendly fashion, as I was mentioning before. So we have, let's say we have a certain data set that defines a probability distribution that then we want to be able to learn and load into a quantum state for then generating samples from that quantum state that resemble the original distribution. So here you can see the distribution of the bars striped data set that I mentioned before, which is a uniform value for the probability for the bars stripes patterns and the zero probability for the other images that don't display the pattern that we are interested in. And so we want our model to be able to learn this probability distribution and exactly produce these patterns. How does the QCBM work to obtain this result? So it starts from a vector of parameters that we can initialize and use in a quantum circuit, in a parameterized quantum circuit, which then is able to transform an initial qubit state to a final output state depending on the parameters. And this final output state contains a probability distribution. So the wave function amplitudes encode a probability distribution according to Born's rule, and then measuring the quantum state in the computational basis, we are able to obtain some quantum outcomes, quantum measurements, that we can compare with the target distribution of the data set. So the idea is to estimate the mismatch between the quantum outcomes and the data, the target data that we have, and use a classical optimizer to minimize this mismatch, which is encoded into like a well-suited wave function that one, cost function that one can define. So the idea is exactly to use a classical optimizer to iteratively update the parameters of the quantum circuit and then minimizing the cost and getting to a final result that is able to represent the probability distribution that we are interested in. And this is therefore is an inherently hybrid architecture because we have a parameterized quantum circuit that is meant to be run on the hardware. Sorry, on the quantum hardware, on the QPU, whereas the classical optimizer is an entirely classical CPU kind of task. So there are a lot of components that are involved in this problem, in this algorithm. So one thing that I want to mention is the fact that there's a first step in which you need to map your data set to qubits. And in this case, we have 2x2 images, which are black and white. So it's kind of straightforward to map 1 qubit to 1 pixel. But there are other cases in which this is less easy, and it's part of the, it's actually like a big part of the development of the algorithm. But other things that can be tweaked and chosen by the developers and the users are the cost function that you can define. So here we decided to use this clipped negative log likelihood, but this is not the only choice, absolutely. And also the classical optimizer, there's a variety of optimizers available, obviously, either gradient based or gradient free, evolutionary strategies, like a lot of different options are available. But also on the quantum side, you can specify the initial state and you have to prepare that. You can choose what backend to use, so either a simulator or a hardware, like if you have that available. And the choice of the backend also affects the choice of the answers of your circuit, meaning how many qubits, what is the connectivity that you can use between the different qubits, which gates are the best to use. And then there are also a lot of other different things that you can choose in the quantum model, like noise models and error mitigations, these kind of things. So there are a lot of different components. In our case, we decided to use this type of ansatz that considers layers of single qubit rotations and then XX entangling gates, which are ion trap native gates. And this is going to be clear in the following why we chose these gates. And the point is that if we try to orchestrate all of these components using our platform, we are able to actually train our model to be able to get the target distribution learned, and therefore to be able to generate the patterns that we are interested in. Here in the training, you can see that the cost function gets minimized and gets closer and closer to the expected value, as well as the final, the target the measured distribution from our quantum state gets closer to the target. And this is also shown by the fact that we highlight the patterns that we are generating that we can sample from our quantum state here on the right, and we see that they are mostly the ones that we are interested in, with the bars and the stripes, and all the way to the end where the distribution is even more stabilized. So we were able to train our model to reproduce this bars and stripe distribution. This is like promising method, but one of the challenges now in this approach of quantum machine learning is actually how do we scale to larger data sets? That is, this problem is relevant for business applications, but at the same time, it's a big challenge, not the only one about this framework. And it is a big challenge because, as you can, maybe we can have an intuition of that with thinking about the qubit mapping that I mentioned before. So if we map one single pixel of an image to a single qubit, we can easily understand that as we want to consider larger images, then this becomes like soon impossible and unfeasible if we have this mapping with these devices. So we need a new strategy to get we need a strategy to be able to deal with larger data sets. So how do we address this challenge to scale up to larger data set? So first of all, let me tell you like a couple of data sets that could be interesting for our use cases. One is the handwritten digits data set. So the so-called MNIST data set is very widely used in machine learning. So it contains images of handwritten digits and black and white. And then there are also other data sets that can be interesting that may come from real data, especially in the financial domain. So for example, distribution of prices, of stock market prices. So what is the idea that the paradigm that we are considering for our quantum machine learning model here to scale up to larger data set is, this is simply the idea of keeping the dimensionality of the quantum model low, because this is a limitation that we have from the hardware, and incorporate this model into a workflow that contains pre and post-processing classical machine learning steps that are responsible for compressing and decompressing the data. So the idea is to use our QCBM wrapped in a more complex machine learning architecture, which is classical. So let me explain what is the architecture that we use. So let's start with the generative adversarial network. I don't know if you're familiar with that, but like this architecture has different components. There's the generator, which is responsible for generating images, and it starts from sampling from this prior distribution that gives some variety from which the generator sampled to create some images, which this prior is usually chosen to be a random uniform distribution, so like just noise. And therefore, at the beginning of the training, the generator is just able to generate noise. And the task of the discriminator instead is to recognize that the images generated by generator are fake, whereas the images coming from the real dataset are actually real. And so in an adversarial game between generator and discriminator, the generator learns to generate better and better images as the training progresses. And just as a note, the generator and discriminator are both meant to be assumed to be deep networks. So this is the generative adversarial network framework, but we can enhance these going to the associative adversarial networks framework, which comes out from these observations. So if you look at the prior, we said that it's usually meant to be uniform distribution. So the generator learns how to generate images sampling from this uniform kind of space. But then if we look at the discriminator, especially in one of the latest layers, this one is called latent space and provides a compressed representation of the data, especially of their features. So when we feed real data into the discriminator, the observation is that this latent space is far from being uniform. There is a very clear structure that depends obviously on the data that we are using. And so the idea is, can we use this information about the structure of the latent space in the prior in such a way that the generator is able to sample from this space in a more efficient way, and therefore to generate hopefully better data. This is the idea of the associative adversarial network, in which the prior is trained, is represented as modeled as an RBM, so a classical generative model, to learn the structure that is in the latent space, and it's trained. It's also trained during the architecture training, and since it's able to learn the structure, the result is that it can generate better data. Now, since the point here is that this latent space as a reduced dimensionality, as I was saying, is a compressed layer, therefore it's suitable for to use these for quantum enhancement in an ISK-friendly manner, in the sense that if we have a small dimensionality, we can hope to use a quantum model which is amenable for these devices to model this prior distribution. And this is exactly our proposal that we published on the arXiv last week, that is called Quantum Circuit Associative Adversarial Network, which just consists in using a QCBM, the QCBM that I described before, as the prior for the generator. And this QCBM that I described before assumed that the measurements of the quantum state are performed in the computational basis. But here we also proposed kind of an enhanced approach that we called multi-basis QCBM, in which we can exploit the unique property of the quantum state to be able to encode a probability distribution in different bases. So the idea is that we also want to measure the output state in other bases than the computational one. And so we introduced these two variants. One is the orthogonal basis QCBM, in which we also measure in the Y basis, and the trainable basis, in which these rotations that are put in front of the measurements to change the basis measurements are actually free, and they are learned during the training of the hybrid architecture. This means that this whole framework is also able to learn what is the best basis to use for getting information from your quantum state. And this is like the enhanced kind of approach of the QCBM compared to what I described before. So let me, so we, in this case, even more components are involved, as it's clear from the difficulty of this explanation of the structure. And so with Orchestra, we were able to explore the different priors that I mentioned. So a simple QCBM or different basis QCBM options, but also the classical RBM of the associative adversarial networks and the uniform classical GAN. Like easily recycling part of the code that we wrote. So it's easy to swap between this framework, and it's also easy to swap between different backends. So we are able to run this model on simulators, but also on actual real quantum hardware from IonQ. So by running this model, we were actually able to obtain the first high resolution images using a quantum computer. So let me show the results that we obtained using the Ion Trap IonQ computer. And here I'm showing as a measure of the performance, the inception score, which is a popular metric to assess performances of GANs, which measures both the quality of the output of the generated images, but also the diversity. And we can see how this inception score improves during the training for both classical simulation, so DC GAN simulation, the squares, but also for quantum simulations on simulators, so the triangles, or on the actual hardware, the hexagons. So as the training proceeds, we can see that at the beginning, there's a very blurry image that we can produce, but as the training proceeds, we can see that the generator, so the model, gets better and better at generating images all the way to the end, in which we are actually able to obtain an image of digits which resembles the data set. So with Orchestra plus the IonQ hardware, we were able to obtain a result that is really promising, in the sense that with a QCBM, we were able to get a better GAN. And far from being like a claim of quantum advantage, nonetheless, this result is a very promising result, and is a very big step forward in the context of quantum machine learning with complex and full-scale machine learning data set, as you can see here, by comparing the results that we obtained, that we just published, and the state of the art in generating high-resolution digits with a quantum computer. So this indeed is a very promising result, which for sure requires more study and more benchmarks and to assess limitations and performances, but for sure this is a very promising direction that we are excited to explore and continue to study. And if you are interested in learning more about this, I invite you to check out our website, zapatacomputing.com, but also the Orchestra website with the documentation, where you can also find more information about the tutorial that I just explained about the QCBM. And with this, I would like to thank you for the attention, and happy to take any question if there is some.
Thank you. Thank you for your excellent talk. Let me see if there is any question. I do have one. It's about if you have any idea, if you have tried to compare with a generative mode of quantum annealers.
So actually, all the simulations were just on a gate-based model, in the sense that the QCBM itself is a gate-based idea.
Yeah, so you have because the kind of problem you can try to solve can be very similar. So I was wondering if you have any benchmark to compare the two methods.
No, we just focused on the gate-based approach, but for sure it could be interesting to see how these work on the deep wave or kind of quantum annealers approach. But we haven't tried. We're more focused on the challenges for the gate-based paradigm. I would say.
I see a question. Did you try introducing some noise such as introducing a pixel in the picture, and if you have, how it performs.
Okay, so actually, all the simulations were, so since I showed like the state of the art before our work was like not very promising, was not very not a very good result. So we didn't try yet to add noise, because we wanted to try if we were actually able to improve these. So this is like the first step of a certainly more in-depth study that is needed, and I think it's super interesting to proceed in this direction. But this is like just like an initial step, and therefore like we didn't try with noise, but it's definitely an interesting direction to explore. But this was just, you know, like, can we actually do something interesting with this new model? Like, can this work? So this is promising, and it paves the way for additional studies for sure.
So let's thank the speaker again.